Right now, you are falling through a hole in space 2 billion light-years wide. Scientists confirmed this in 2013, and most people still have no idea. We live inside the KBC void, a cosmic desert where matter is 20% thinner than it should be. That emptiness is warping our measurements of reality itself, making the universe appear to expand faster here than anywhere else, and breaking our most fundamental equations. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, were mapping 35,000 galaxies across billions of light years when they noticed something wrong. Everywhere they looked near Earth, there were fewer galaxies than expected. Not slightly fewer, 20% fewer. The pattern stretched outward in every direction for 1 billion light years, forming a vast sphere of cosmic emptiness with us near the center. This was not a small gap between clusters. It was a void on a scale that standard cosmology said should not exist. The researchers triple-checked their data, used multiple galaxy surveys, and examined the sky from different angles. The result held every time. Our galaxy sits inside an underdense bubble so massive, it dwarfs everything else ever observed. The discovery earned a name using the initials of its 3 discoverers, the KBC void. But there is nothing casual about what it represents. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster and leave empty spaces between them, that is expected. But a region this enormous, with such a significant deficit of matter, pushes the boundaries of what random chance can explain. Computer simulations of cosmic evolution rarely produce voids this large and this empty. When they do, it requires exceptionally rare initial conditions. Some scientists calculated the statistical probability at less than 1 in 1,000, a 10 sigma deviation from average density, meaning you might not find one anywhere in the entire observable universe. Yet here we are, living inside one. The implications cascaded immediately. If we live in such an unusual location, does that bias every measurement we make? When we point telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate, or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology: the Hubble tension. For years, scientists have measured 2 different expansion rates depending on whether they study the ancient or the nearby universe. One method examines the cosmic microwave background, ancient light from when the universe was just 380,000 years old. That gives an expansion rate of about 67 kilometers per second per megaparsec. The second method uses nearby supernova and Cepheid variable stars as cosmic measuring sticks, comparing their known brightness to their apparent brightness to calculate distances. That local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise. Both should give the same answer. They do not. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it, adding extra velocity to their motion away from us and making local expansion appear faster than average. Suddenly, the conflicting measurements make sense. We are not measuring the universe incorrectly. We are measuring it from inside a hole. Cosmic voids are not truly empty, which makes them stranger than their name suggests. Between their lonely galaxies stretches space containing mainly dark matter, dark energy, and occasional wisps of hydrogen gas. Density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. In dense regions full of galaxies, Gravity fights against dark energy, slowing local expansion. Inside voids, gravity loses that tug of war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe, growing like bubbles, pushing their boundaries outward while surrounding filaments of galaxies act as walls. The more a void expands, the emptier it becomes, which allows even faster expansion. Scientists confirm this through careful observation. Galaxies near void edges move faster than cosmic expansion alone would explain. Something is pushing them outward, the gravitational pull from all the matter outside the void. Think of it as a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley. But in space, that pull makes galaxies fall outward, not inward. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by this gravitational imbalance. This also leaves fingerprints on the cosmic microwave background. Light passing through voids experiences less gravitational influence than light traveling through normal space. When astronomers study the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. These cold spots line up perfectly with where we observe large voids today. That alignment is not coincidence. It is physics. The universe is not a smooth soup of evenly distributed galaxies. It resembles Swiss cheese, dense matter forming walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at intersections where filaments meet, creating nodes of intense density. Stretching between them run long chains of galaxy groups extending for hundreds of millions of light years. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure was not always obvious. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much cosmic expansion had stretched its light toward redder wavelengths. The universe had structure on scales nobody expected. The Sloan Digital Sky Survey, begun in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show filaments twisting like blood vessels, and voids appearing as dark bubbles, sometimes 500 million light years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light years long. On the opposite extreme, supervoids like the Eridanus Void stretch 1.8 billion light years wide, with even fewer galaxies than the KBC Void. Galaxies are not the fundamental building blocks. The web itself is the structure. Galaxies just mark where matter happens to concentrate. The answer reaches back to the very beginning. Immediately after the Big Bang, matter was not perfectly uniform. During inflation, an exponential expansion in the universe's first tiny fraction of a second, quantum fluctuations were stretched from subatomic scales to cosmic scales, creating slight variations in density. Some regions were a tiny bit denser than average. Others were slightly less dense. The variations were minuscule, about 1 part in 100,000. But gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, underdense regions expanded into voids. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness, punctuated by occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble, and that makes all the difference. The Milky Way is not at the center of the KBC void, but it is close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. The void extends outward for 1 billion light-years in every direction from that center, so our offset is relatively small. We sit well within the underdense region, surrounded by low density in all directions. Our larger cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, about 80 galaxies, including our giant neighbor, Andromeda. The local group sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The KBC void is so vast it can swallow entire superclusters and still have room to spare. Our galaxy is also influenced by a nearby smaller feature called the local void, distinct from but connected to the larger KBC void, extending about 200 million light-years. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This is a peculiar velocity, driven by local gravitational effects rather than the stretching of space itself. When scientists measure galaxy motions out to 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions of space are moving faster than they should, flowing in coherent patterns driven by the void's gravitational imbalance. Galaxies are not just sitting in an empty region passively expanding with the universe, they are actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. Every measurement you have ever heard about the universe's expansion rate might be wrong, not because scientists made mistakes, but because we are measuring from inside a cosmic hole that distorts the signal. The discrepancy between 67 and 73 kilometers per second per megaparsec has reached 5 sigma statistical significance, less than a 1 in a million chance it is random variation. This is the Hubble tension, and it represents a fundamental challenge to our understanding of cosmic evolution. The KBC void explains why these numbers disagree. When we measure expansion using nearby supernovae, we are measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity, inflating the local measurement. We are not measuring the universe's true expansion rate. We are measuring expansion plus the void's peculiar velocity field. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. But here is where it gets uncomfortable. If the void explains our local measurements, then those measurements may be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special position and the universe looks roughly the same from any vantage point. Science has progressively decentered humanity. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And now we are supposed to believe we just happen to live inside one of the largest voids ever observed? The statistical improbability bothers many researchers. Yet the evidence keeps mounting. The void exists. Our measurements are discrepant. The void's effects match the observations. Whether we like the implications or not, our location may be causing us to misinterpret what we measure. The Hubble tension is not just an inconvenient disagreement. It represents a fundamental challenge to the lambda cold dark matter model, the standard framework of cosmology that has been spectacularly successful for decades, explaining cosmic microwave background fluctuations, the abundance of light elements, galaxy formation, and large-scale structure. The tension matters because the expansion rate determines everything about cosmic history. If the universe expands faster, it reaches its current size in less time. Current calculations place the universe's age at 13.8 billion years. But if the higher local measurement applies globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old based on stellar evolution models. Those stars would be older than the universe itself, which is impossible. The tension also affects our understanding of dark energy, which makes up about 68% of the universe's total energy content. If the expansion rate is higher than we thought, dark energy's behavior might differ from current models. Some researchers propose dark energy evolves over time rather than remaining constant. Others suggest new physics in the early universe. Every proposed solution introduces new complications. Dozens of alternative explanations have been tested. Perhaps dust between galaxies dims supernovae more than accounted for, inflating the expansion rate. Perhaps Cepheid stars behave differently in different environments. These keep getting ruled out as measurement techniques improve. Others suggest modifications to general relativity, but Einstein's theory has passed every other test thrown at it. The void hypothesis offers a cleaner solution requiring fewer assumptions. It simply states that we are in an unusual location and our local measurements reflect that, rather than reflecting universal properties. Recent work has strengthened this hypothesis by showing it naturally predicts other observations. The outflow velocity should affect not just the expansion rate, but also the motion of galaxy clusters in our vicinity. Measurements of those bulk flows match the void predictions. Nevertheless, debate continues. Not all cosmologists accept the void explanation. Some argue even a void as large as the KBC cannot produce a big enough effect to fully explain the tension. The controversy remains unresolved, which is why the Hubble tension continues to be called a crisis. Gravity inside a void does something counterintuitive. It pushes outward instead of pulling inward. Not because gravity reverses, but because of geometry. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, away from the valley center. Inside a cosmic void, galaxies experience the same effect. All the matter lies outside the void in surrounding filaments and clusters. That exterior matter gravitationally attracts interior material, pulling galaxies outward from the void center toward denser regions beyond. The result is an outflow, a systematic pattern of galaxies accelerating away from the underdense region. Astronomers can track this using redshift measurements combined with distance estimates. The pattern is clear. Galaxies near void centers move faster outward than cosmic expansion alone predicts. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. This creates a systematic bias that inflates the apparent expansion rate when measured from inside. Close to the void center, the outflow is rapid. Farther from the center, but still within the void, the outflow is slower. Beyond the void's edge, peculiar velocities might even reverse as matter falls back toward denser filaments. This predicts that the Hubble constant should appear to decrease with distance. And recent observations confirm exactly that trend. Modeling these effects shows that a void roughly 1 billion light-years in radius with a 20% density deficit can easily produce the observed velocity anomalies. The standard cosmological model, however, struggles to explain how such a large void formed in the first place. This raises a troubling possibility. Maybe our model is missing something fundamental about how structure forms. The Milky Way is not sitting still. It is plummeting through the cosmos at 600,000 miles per hour, roughly 850 times the speed of sound. This is not from the expansion of space, but from local gravitational effects. Specifically, our galaxy being pulled away from the local void toward denser structures beyond. 600,000 miles per hour means the Milky Way travels about 167 miles every second. In a single year, our galaxy moves about 5.2 billion miles through space relative to the void. But even at this breakneck pace, the void is so vast that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side to the other, and meanwhile the void continues expanding faster than we can escape it. Our galaxy is also falling toward the Virgo cluster, a rich concentration of over 2,000 galaxies about 60 million light-years away, adding another component of roughly 250 kilometers per second directed toward Virgo. And the Milky Way and Andromeda are falling toward each other, due for a collision in about 4 billion years. When you add all these gravitational influences together, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame is about 627 kilometers per second. Our high speed through space is itself evidence for the void. If we lived in a typical region, our peculiar velocity would be much smaller, maybe 100 or 200 kilometers per second at most. The fact that we are moving so fast indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large underdense region. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to shatter it. The principle states the universe is homogeneous, the same everywhere, and isotropic, the same in all directions, on sufficiently large scales. These assumptions simplify cosmological mathematics enormously. Without them, the equations become vastly more complicated. The KBC void represents a major violation of homogeneity. A region 2 billion light-years across with a 20% density deficit is a huge inhomogeneity, not small compared to the observable universe. Throughout history, science progressively removed Earth from any special position. Copernicus showed Earth was not the center of the solar system. Later observations showed the solar system was not the center of the galaxy. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the center, there is no center at all. The void challenges that worldview directly. Some scientists calculate that in a universe governed by standard cosmology, the KBC void should be a 10 sigma statistical deviation. So unlikely you might not find one anywhere in the observable cosmos. Yet, we are in one. This suggests either we are incredibly lucky or the standard model is wrong about how structure forms. Defenders of the cosmological principle argue that homogeneity only applies at scales of several hundred megaparsecs or larger, and the void sits right at that boundary. Others argue the void's deficit might be closer to 10 or 15% rather than 20, which would make it statistically less shocking. Others invoke a weak anthropic argument. Perhaps intelligent life forms, preferentially in moderately underdense regions, so finding ourselves in a mild void is not surprising. But a 20% deficit is more than mild. The debate is not settled. Future surveys mapping the universe to greater depths will reveal whether large voids are truly as rare as standard models predict, or more common than expected. Either outcome requires significant revisions to how we think about the cosmos. The KBC void defies probability in a way that makes cosmologists deeply uncomfortable. Standard cosmology predicts the larger and deeper a structure, the rarer it should be. Small voids are common. Large voids are less common. Supervoids the size of the KBC void should essentially not exist. Computer simulations of structure formation using the lambda cold dark matter model rarely produce anything this extreme. When researchers run thousands of simulated universes and look for voids as large and deep as the KBC void, they find very few matches. One analysis calculated a 10 sigma deviation from expected density, incomprehensibly unlikely. You would need to observe trillions of universe-sized volumes to expect to find even one, yet here we are. If the observations are correct, which multiple independent studies suggest they are, then the model must be missing something. Possibilities include initial density fluctuations after the Big Bang were not as smooth as standard inflation models predict. If inflation produced more power on large scales, large voids would form more easily. Structure formation proceeded faster or differently than models predict. If gravity was effectively stronger in the past, or dark matter behaves differently than assumed, structure would form more vigorously. Observational biases have made the void appear deeper and larger than it really is. Different groups using different datasets have measured the void's properties and found somewhat different results. Some find 20%, others find closer to 10 or 15. Future missions like the Euclid Space Telescope and the Vera Rubin Observatory will provide much better data to distinguish between these possibilities. Until then, the void remains a cosmic puzzle that refuses to fit neatly into our current understanding. Cosmic voids are the best places in the universe to study dark energy, because they are the only regions where dark energy dominates completely. In dense areas like galaxy clusters, gravity resists cosmic expansion. Clusters hold themselves together despite the universe expanding around them. But in voids, where matter is sparse, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. Dark energy was discovered in 1998 through observations of distant supernovae. It accounts for about 68% of the universe's total energy, behaving opposite to gravity, pushing space apart and accelerating cosmic expansion. Its exact nature remains unknown. It could be a cosmological constant, an unchanging energy density built into the fabric of space. Or it could be a dynamic field that varies in strength over time and space. Distinguishing between these possibilities requires precise measurements of how expansion accelerates in different environments. Voids provide a cleaner signal than dense regions, where local gravitational effects complicate everything. By measuring how fast voids expand compared to predictions, scientists can test whether dark energy behaves as a constant or changes over time. Void shapes provide additional information. If dark energy is truly uniform, voids should expand equally in all directions, staying spherical. Any distortion would reveal variations in dark energy or unknown forces. Current measurements show most large voids are roughly spherical, supporting uniform dark energy. But the measurements are not yet precise enough to rule out small variations. The expansion history of voids also encodes information about dark energy. By modeling how a void grows over time, given different dark energy properties, and comparing predictions to observations at different distances, which means different times in cosmic history, scientists can constrain what dark energy must be like. Early results suggest dark energy has been roughly constant over the past several billion years, consistent with the simplest models. Galaxies inside cosmic voids grow up in profound loneliness. Unlike galaxies in dense clusters that interact frequently with neighbors, void galaxies evolve in isolation. and that environmental difference shapes everything about them. Void galaxies tend to be smaller and dimmer than galaxies in filaments. They have lower masses containing fewer stars. Their isolation means they rarely experience the galaxy mergers that are common in dense regions. Mergers are a primary driver of galaxy evolution, triggering bursts of star formation and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less developed. There is a surprising twist, though. While most void galaxies form stars slowly, a higher fraction of them are starburst galaxies, experiencing intense, short-lived periods of rapid star formation. The reason is gas. Void galaxies are often unusually gas-rich, retaining large reservoirs of neutral hydrogen that have not yet been converted into stars. In dense environments, interactions strip away gas or trigger star formation, depleting the reservoir. In voids, galaxies keep their gas longer. When star formation finally ignites, triggered by internal processes rather than external interactions, there is plenty of fuel. The result is an intense starburst before the galaxy settles back into quiet. Most void galaxies are late-type spirals or irregular galaxies rather than ellipticals. Elliptical galaxies form primarily through mergers, which are rare in voids. Without mergers, galaxies maintain their disk structures and spiral arms, sometimes showing remarkably undisturbed morphologies that make them excellent laboratories for studying galaxy evolution in peaceful environments. Below a certain mass threshold, halos in voids cannot retain gas efficiently enough to form stars at all. This explains why voids are not completely filled with tiny dwarf galaxies. The smallest halos exist but remain dark, containing only dark matter and no visible galaxies. The intergalactic medium in voids remains cooler and denser than in clusters, closer to early universe conditions, making voids excellent laboratories for studying primordial gas. The isolation is self-reinforcing. With no rich clusters to pump energy into the intergalactic medium and no massive galaxies to drive strong winds, the void remains quiet and underdeveloped indefinitely. The Laniakea supercluster is a mind-bending structure that redefines what we mean by our cosmic neighborhood. Identified in 2014, Laniakea contains roughly 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian and means immeasurable heaven, fitting given its scale. The Milky Way sits on Laniakea's outskirts, part of a vast cosmic drainage basin where galaxies flow toward a central gravitational attractor called the Great Attractor. Here is the paradox. Laniakea, despite containing 100,000 galaxies, resides entirely within the KBC void. How can a supercluster, one of the largest bound structures in the universe, exist inside an underdense region? The answer lies in how density is defined. The KBC void is underdense compared to the cosmic average when measured over very large scales. But it is not uniformly empty. It contains filaments, which contain clusters, which contain groups, which contain galaxies, which contain stars. Structure exists at every scale. The void is primarily defined by the absence of rich superclusters and large clusters at its center. Laniakea occupies part of that volume, large compared to typical superclusters, but small compared to the void itself. The gravitational flows within Laniakea provide some of the best evidence for how gravity organizes matter. By mapping galaxy velocities in and around the supercluster, astronomers constructed a three-dimensional flow map. Everything moving toward the Great Attractor is considered part of Laniakea. Everything flowing away belongs to neighboring structures. The Milky Way's peculiar velocity points toward the Great Attractor, confirming we are gravitationally bound to Laniakea. But Laniakea itself is falling towards something even larger, the Shapley supercluster, located about 650 million light-years away. It is the most massive structure in our region of the universe, and its gravitational pull affects everything around it, including Laniakea. This creates a hierarchy of flows. Galaxies flow toward clusters, clusters toward superclusters, superclusters toward even larger attractors. The KBC void modifies all of these flows by adding an outward component. The measurements revealing all of this rely on a cosmic ruler built from sound waves in the infant universe. Baryon acoustic oscillations are frozen sound waves from the early universe, and they have become the most reliable ruler for measuring cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were coupled together. Sound waves rippled through this plasma, creating oscillations in density. When the universe cooled enough for atoms to form, those waves froze in place. The distance the waves had traveled before freezing, about 490 million light-years, left an imprint on how matter is distributed today, showing up as a characteristic scale in galaxy clustering. Astronomers can measure this scale and use it as a standard ruler because the physics that created it is well understood. It works at any distance. By comparing the apparent size of this scale at different distances, scientists map how the universe has expanded over time. The technique is called Baryon acoustic oscillation analysis, and it has revolutionized cosmological distance measurements. When scientists analyze galaxy distributions in our local region and compare them to predictions from Baryon acoustic oscillations, they find a clear deficit. The void shows up as a region where the observed scale of galaxy clustering differs from what distant measurements predict. This mismatch is exactly what you expect if you are inside an underdense region, providing independent confirmation that the void exists. Galaxies within the void show redshifts slightly higher than expected for their distance when using the Baryon acoustic oscillation ruler, consistent with the outflow velocity adding to the cosmic expansion signal. The Hubble tension is thus not confined to supernova measurements alone. It appears across multiple independent techniques. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. Within a few years, astronomers will know the void's properties to within a few percent uncertainty, either confirming the void as the explanation for the Hubble tension or revealing additional complications that require further theoretical development. The cosmic microwave background radiation fills the entire universe with faint light left over from the Big Bang, with a temperature of 2.7 Kelvin, just above absolute zero. That temperature is remarkably uniform, but tiny variations exist, typically only a few millionths of a degree. Hotspots correspond to regions that were slightly denser in the early universe, cold spots to slightly less dense regions. But the cosmic microwave background also reveals evidence of cosmic voids through an effect called the integrated Sachs-Wolf effect. When light from the cosmic microwave background passes through a void, it experiences less gravitational influence than light traveling through dense regions. As a photon traverses the expanding void, it ends up with slightly less energy than it started with, showing up as a temperature drop. The effect is tiny, but detectable. Astronomers identified large void locations using galaxy surveys, then looked at the cosmic microwave background temperature in those directions. On average, the temperature is about 10 millionths of a degree cooler than the cosmic average, statistically significant and matching theoretical predictions. Voids do affect the cosmic microwave background. For the KBC void specifically, the effect should be particularly strong because of its enormous size. Light from the cosmic microwave background passes through nearly the entire void on its way to us. accumulating the temperature deficit over the full billion light-year extent. One of the most intriguing features in the cosmic microwave background is the cold spot. A region about 5 degrees across on the sky, roughly 100 millionths of a degree cooler than surrounding areas, discovered by the Wilkinson Microwave Anisotropy Probe in 2005. Its size and temperature deficit are statistically unusual, occurring in only about 2% of simulated universes. Some researchers initially proposed exotic explanations, including a collision with another universe in a multiverse. A more conventional explanation emerged when astronomers found evidence for a large underdense region in that direction, the Eridanus supervoid, about 3 billion light-years away and roughly 1.8 billion light-years across. Calculations show this void can account for about half the observed cold spot anomaly through the integrated Sachs-Wolf effect. The other half might come from a chance alignment with a cold fluctuation in the primordial microwave background. The KBC void does not align with the cold spot. It surrounds us in all directions. Its temperature signature is more subtle, showing up as a modification to the overall pattern rather than a localized anomaly. Multiple independent lines of evidence point to the same basic picture. We live in a large underdense region with significant but not extreme properties. The standard theory of gravity is Einstein's general relativity, formulated in 1915. It has passed every test for over a century. But the KBC void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity, perhaps gravity does not work exactly as Einstein predicted on the largest scales. The most prominent alternative is modified Newtonian dynamics, or MOND, proposed in 1983 by physicist Mordechai Milgrom. MOND suggests that at the tiny accelerations relevant for galaxy outskirts and cosmological scales, gravity becomes stronger than general relativity predicts. Originally proposed to explain galaxy rotation curves without dark matter, MOND has struggled with many cosmological observations. But it performs better than expected at explaining some features of the cosmic web. In MOND cosmology, structures form more efficiently because enhanced gravity on large scales pulls matter together more effectively. Computer simulations using MOND gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. The statistical improbability disappears. The void becomes an expected consequence of how structure forms under modified gravity. However, MOND faces serious challenges. It struggles to explain cosmic microwave background temperature fluctuations that standard cosmology explains beautifully. It also cannot easily account for gravitational lensing observations, where massive galaxy clusters bend light from background galaxies. The amount of lensing observed requires more gravity than visible matter, plus MOND can provide, suggesting dark matter is still needed. Some researchers have developed hybrid models combining MOND with a small amount of dark matter, typically in the form of neutrinos. These neutrino hot dark matter cosmologies can explain both the cosmic microwave background and enhanced structure formation. Other modified gravity theories introduce additional fields or higher dimensional effects that alter gravitational dynamics on cosmological scales while preserving general relativity's successes on smaller scales. Some predict gravity becomes effectively stronger in low-density regions, like voids, making large voids easier to form. Proponents of modified gravity point to the KBC void, the Shapley supercluster, the Sloan Great Wall, and other enormous structures as evidence that structure formation is more vigorous than lambda cold dark matter predicts. Defenders of standard cosmology counter that modified gravity theories have their own problems, and that invoking them to solve one puzzle often creates new ones elsewhere. Future observations should help settle this. If large voids and extreme structures turn out to be more common than currently thought, modified gravity becomes more appealing. If they remain rare, the standard model survives, but leaves us with the uncomfortable conclusion that Earth occupies a genuinely special location. The age of the universe is one of cosmology's most important numbers, and the KBC void puts it in jeopardy. Current measurements based on the cosmic microwave background place the universe's age at 13.8 billion years. But if the local expansion rate is genuinely faster than the cosmic average due to the void, those models could be wrong. If the locally measured Hubble constant of 73 kilometers per second per megaparsec represents the universe's true expansion rate, the universe reached its current size in less time. Calculations show this would make it about 8% younger, roughly 12.7 billion years old, instead of 13.8 billion years. That creates an immediate problem. The oldest stars in globular clusters appear to be about 13 billion years old, based on stellar evolution theory. You cannot have stars older than the universe itself. The ages come from understanding how stars evolve. By observing which stars have reached the end of their lives in a globular cluster, astronomers estimate when that cluster formed. The oldest clusters show their most massive remaining stars are just barely still alive, indicating formation about 13 billion years ago. White dwarf cooling times provide an independent check. White dwarfs cool gradually over billions of years. The coolest white dwarfs we observe have been cooling for about 12 to 13 billion years. These measurements do not depend on stellar evolution models, making them harder to adjust. The Gaia space mission has revolutionized these measurements by providing precise distances to globular clusters through parallax measurements. The improved results confirm the oldest clusters are indeed about 13 billion years old. The most likely resolution is that the void inflates our local expansion measurements. If the cosmic microwave background estimate of 13.8 billion years is correct, the universe is old enough for the observed stars and white dwarfs to exist. This requires accepting we live in an unusual location, which bothers some scientists philosophically, but avoids requiring major changes to stellar physics or cosmology. However, if dark energy has evolved over time, weaker in the past and stronger recently, the early expansion would have been slower, and the universe would be older than the high local Hubble constant suggests. This scenario remains speculative, but cannot be ruled out. Galaxies are not stationary. They move through space in response to gravity from surrounding structures. In standard cosmology, these peculiar velocities should be relatively small and random on large scales, averaging out over volumes hundreds of millions of light years across. Observations tell a different story. Measurements of galaxy velocities using multiple techniques show significant bulk flows extending to distances of 200 to 300 million light years, reaching velocities of 400 kilometers per second or more, far higher than standard cosmology predicts. These flows are coherent, meaning galaxies across huge volumes are all moving in roughly the same direction. The KBC void is exactly the kind of structure that could produce such flows. Material within the void accelerates outward toward denser regions beyond the void's edges, creating a bulk flow pointing away from the void center. The Cosmic Flows Project has created the most detailed maps of bulk flows to date. The observed patterns match predictions from models that include the KBC void. Flows strongest near the void edges where the density gradient is sharpest, directed outward towards surrounding filaments, with magnitudes depending on the void's depth and size. A 20% density deficit extending a billion light years produces flows of about 400 kilometers per second, exactly what is observed. Standard cosmology without a void struggles to explain these flows. Simulations predict bulk flows should decline rapidly with scale. By the time you average over 200 million light-years, they should be under 100 kilometers per second. The observed flows are 4 times larger. Some cosmologists view this as evidence that lambda cold dark matter is missing something. Alternative theories like modified gravity naturally predict stronger bulk flows because they enhance structure formation. Upcoming surveys will measure bulk flows at even larger distances. If flows remain strong beyond 300 million light-years, it would further challenge standard cosmology. The KBC void is not the largest underdense region known. That distinction belongs to the Eridanus supervoid, discovered through its impact on the cosmic microwave background. Located in the constellation Eridanus, this void is roughly 1.8 billion light-years across. What makes it particularly intriguing is how it was found, not by counting galaxies, but by noticing an unusually cold spot in the cosmic microwave background temperature map. The cold spot, about 10 degrees across, roughly 70 millionths of a degree cooler than average, was discovered by the Wilkinson Microwave Anisotropy Probe in 2005. It puzzled cosmologists because its size and temperature deficit are statistically unusual. It persisted in multiple independent datasets, including observations from the Planck satellite. When astronomers surveyed the galaxy distribution in that direction, they found evidence for a large underdense region roughly aligned with it. The Eridanus supervoid sits about 3 billion light-years away. Light from the cosmic microwave background passes through this void, losing energy through the integrated Sachs-Wolf effect, showing up as a temperature deficit. A void of this size and depth can account for about half the observed cold spot anomaly. The Eridanus supervoid raises the same questions as the KBC void. How did such a large underdense region form? Is it consistent with standard cosmology? Its existence was effectively predicted by the cosmic microwave background cold spot before it was confirmed by galaxy surveys. But measuring its precise properties remains difficult because of its great distance. If both the KBC void and the Eridanus supervoid are real and as extreme as measurements suggest, it raises the likelihood that such voids are more common than standard cosmology predicts. Finding 3 or 4 comparable structures would become increasingly difficult to explain through the standard model. Future deep surveys will map the universe to greater distances and discover more voids, testing whether the statistical distribution of void sizes and depths matches predictions. The term Hubble bubble has emerged to describe a troubling observational pattern. When astronomers measure the Hubble constant using nearby objects, supernovae within about 2 billion light-years, they get higher values around 73 kilometers per second per megaparsec. When they use objects farther than 2 billion light-years, or rely on cosmic microwave background data, they get lower values around 67 kilometers per second per megaparsec. The boundary at roughly 2 billion light-years is suspiciously close to the edge of the KBC void. Researchers propose that measurements within the void are affected by its presence, creating a bubble of biased observations. Only by looking beyond the bubble can we see the universe's true expansion rate. This hypothesis makes a clear prediction. The measured Hubble constant should vary with distance. Nearby measurements should show the highest values. As you look farther out, approaching and crossing the void's edge, the measured value should decline toward the cosmic average. Recent observations are beginning to show exactly this. Studies using supernovae at various distances find that the inferred Hubble constant decreases with redshift. The trend is not yet definitive, but the direction matches predictions. If the bubble is real, it creates a significant problem. Most measurements of the local expansion rate necessarily use nearby objects, because those are the only ones we can observe in sufficient detail. This means our most reliable local measurements are exactly the ones most affected by the void. It is like trying to determine Earth's global climate by only measuring the temperature inside a heated building. You can make very precise measurements, but they do not represent the global average. Breaking out of the bubble requires observing objects beyond 2 billion light-years with comparable precision to nearby objects. The James Webb Space Telescope can observe distant supernovae with unprecedented detail. Early results suggest the far universe expands at the rate predicted by the cosmic microwave background, consistent with the bubble hypothesis. But more observations are needed. Multiple independent lines of evidence point to the same conclusion. Our local environment, within about 2 billion light-years, differs systematically from the universe at large. We live in an island of unusual properties, surrounded by a more typical cosmos. Cosmic voids act as filters, preventing certain types of structures from forming within them. In dense regions of the cosmic web, galaxies collide and merge frequently, triggering bursts of star formation and feeding supermassive black holes, transforming small irregular galaxies into massive ellipticals over billions of years. Rich galaxy clusters form as groups merge under mutual gravity. In voids, this trajectory is blocked. The low density means gravity is weak. Small structures like galaxies can form because the initial density fluctuations that seeded them were strong enough to overcome cosmic expansion. But larger structures like massive galaxy groups or rich clusters require more gravity than voids can provide. Matter density is simply insufficient to pull together such massive concentrations. As a result, voids remain perpetually underdeveloped, stuck in an evolutionary state that dense regions passed through billions of years ago. This creates a ceiling on structure development. The largest structures that form within them are modest galaxy groups containing a few dozen members. This filtering effect has consequences for galaxy evolution. In dense environments, frequent mergers consume gas and shut down star formation. Galaxies become red and dead. But in voids, mergers are rare. Galaxies retain their gas and continue forming stars slowly over billions of years, remaining blue and actively star-forming much longer than their counterparts in clusters. The filter is self-reinforcing. With no rich clusters to pump energy into the intergalactic medium and no massive galaxies to drive strong winds, the void remains quiet indefinitely. Meanwhile, dense regions continue evolving, becoming richer and more complex, creating increasing contrast between voids and filaments. Dark energy accelerates this trend by speeding up void expansion. This even raises questions about life in the universe. Void galaxies experience fewer catastrophic events like nearby supernovae or gamma-ray bursts that could sterilize planets, providing long-term stability. On the other hand, lower star formation rates mean fewer heavy elements available for planet formation. Whether voids enhance or diminish the prospects for life remains an open question. Dark energy is accelerating the universe's expansion, and that has dire implications for the far future. As space expands faster over time, structures not gravitationally bound together will drift apart and eventually lose all contact. Voids will expand faster than the universe as a whole because they contain less matter to resist the expansion. The filaments surrounding voids will thin out as galaxies within them are stretched farther apart. Eventually, even neighboring superclusters will lose causal contact as space between them expands faster than light can cross. The universe's fate is increasing isolation, structures becoming islands separated by ever-expanding voids. For galaxies within voids, this isolation will be profound. Currently, galaxies in the KBC void can still see the surrounding filaments and clusters. But as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us. The cosmic horizon will shrink over time. Objects currently visible will fade as their light gets redshifted into invisibility. Galaxies deep within voids will find themselves in increasingly empty skies. The cosmic microwave background will become cooler and dimmer as its photons stretch to longer wavelengths. Eventually, it will become undetectable. This raises a disturbing question for future civilizations. If a civilization arises in a void galaxy billions of years from now, what will they be able to learn about the universe? Their sky will be nearly empty except for their local group of galaxies. The cosmic microwave background will be too faint to detect. There will be no evidence of the Big Bang. No distant galaxies to measure cosmic expansion. No supernovae to trace the acceleration. They will be cosmologically isolated, unable to observe the larger universe because light from beyond their immediate vicinity cannot reach them. Such civilizations might conclude they live in a static island universe surrounded by empty space, never suspecting the vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is the inevitable consequence of accelerating expansion. Even within our own void, the long-term future looks lonely. The Milky Way and Andromeda will merge in about 4 billion years, forming a giant elliptical galaxy, sometimes called Milkomeda. This merged galaxy will be the dominant structure in our local group, but the local group itself will become increasingly isolated. Other nearby groups and the Virgo cluster will recede beyond our cosmic horizon within tens of billions of years. Milkomeda will find itself essentially alone in an expanding void. Star formation will gradually cease as gas is consumed or expelled. The galaxy will fade, containing only old red stars and eventually just white dwarfs, neutron stars, and black holes. The universe we inhabit is vast, strange, and mostly empty. We live in a cosmic desert that warps our perception of reality itself. The KBC void is not just an inconvenient statistical anomaly. It is a window into the deepest questions about the nature of space, time, gravity, and our place in the cosmos. Every measurement we make, every theory we build, carries the fingerprint of where we happen to find ourselves, falling through a hole in space 2 billion light-years wide. Right now, you are falling through a hole in space 2 billion light-years wide. Scientists confirmed this in 2013, and most people still have no idea. We live inside the KBC void,